Okay, everyone, let's get started. Today we're gonna discuss two very important sections. Okay, section 2.2 is the counting method. Okay, it's very important and also very useful. We're gonna learn what is combination and what is so-called permutation. Section 2.3 is conditional probability. Okay, so we're gonna learn about this new concept. All right. Right, let's see, assume we have k operations, so k steps to perform experiment. Okay, if there are n1 ways to perform the first step, the first operation, and for each of these n1 ways, there's n2 ways to perform the second calculation, the second step, second operation, and so on. Then the total number of ways to perform the sequence of these k operations is n1 times n2 times n3 times nk. Okay. For example, if we toss a coin, we toss 3 coins, then the total number of simple events will be 2 times 2 times 2. Okay, because we can think of this toss a 3 coin as an experiment with 3 steps or 3 operations. Okay, the first step is toss the first coin. So we have 2 possible outcomes. We could have head or tail. So that is 2. And the second coin also has 2 possible outcomes, head and tail. Okay, so 2 times 2 times 2, so totally we have 8 possible outcomes. Okay. If we toss 2 dice, okay, for each dice we have 6 possible outcomes. Right? We could have 1, 2, 3, 4, 5, and 6. Then the total number of simple events gonna be 6 times 6. Okay, so 2 steps. The first step we have 6 possible outcomes, which is the outcome of the first dice. And for each of these outcomes, we also have 6 possibility. 1, 2, 3, 4, 5, 6. So totally we have 36 simple events. Here's another example. We have 2 M&Ms drawn from a dish containing 2 red and 2 blue candies. Okay. And then the total number of simple events will be 4 times 3. So why is 4 times 3? Okay. We have 4 candies in that dish. Step 1, we pick 1 from these 4. Okay, so we have 4 possible outcomes. But after first pick, we have 3 candies remaining. So the second pick, we only have 3 possible outcomes. So 4 times 3, okay, 12 possible outcomes for this experiment. Okay, so that's the simple examples of counting method. And let's continue. When ordering a certain type of computer, there are 3 choices of hard drive. Okay, 4 choices for amount of memory, 2 choices for video card, and 3 choices of monitor. Okay, so the question asking how many ways can the computer be ordered? So the equation gonna be based on the counting method. So we can think this as experiment with 1, 2, 3, 4 steps. Okay, so the first step we pick hard drive. Okay, for the hard drive we have 3 choices. And then the second step we choose the memory. For the memory we have 4 choices. Okay, and so on. 2 choice of video card and 3 choice of monitor. Okay, so this is how many ways that computer can be ordered. Okay, so we first think about how many operations, how many steps to finish this experiment. In that case, this is order a certain type of computer. Okay, for the first step, we have 3 choice. Second, 4. So 3 times 4 times 2 times 3. Okay, all right. Okay, and then let's introduce the idea of permutation. Okay, so 5 lifeguards are available for duty on Sunday afternoon. There are 3 lifeguard stations. Okay. Asking how many ways can the 3 lifeguards be chosen and ordered among the 3 stations. Okay, so again, for this experiment, we can think this as how many steps to finish this experiment. Okay, so we have 5 lifeguards. Okay, so 5 person. Sorry for the drawing. It's hard to draw on the laptop. And also we have 3 stations. Let's see, this is station 1, station 2, and station 3. Okay, so the first step is we choose these 5 lifeguards. Let's give the different name, A, B, C, D, E. Okay, so we pick 1 lifeguard for station number 1. Okay, how many ways we can do that? So we have 5 ways to do that. And so that's the first step. Then the second step is we choose another lifeguard for station 2. So that's the first step. This is the second step. In the first step, we have 5 ways to do that. For the second step, because we pick 1 lifeguard already, we have 4 remaining candidates. So we have 4 choices only. So 5 times 4. Okay. And then for the third station, we only have 3 lifeguards to choose. Okay, so 5 times 4 times 3. Okay, so 60 different ways. All right. So in general, we can give an equation for that, which is permutation. Sometime the character will change in the PowerPoint to the PDF. So permutation is read as P and K. Okay, so P and K is equal to so N with exclamation point, which we call that factorial of N. So we call that factorial of N. So that is equal to N times N minus 1 times N minus 2, okay, and times 1. Okay, so that is factorial of N. And so does N minus K, factorial of N minus K is equal to N minus K times N minus K minus 1 times 3, 2, and 1. Okay. So what is permutation, and where we can use permutation equation for the counting method? So permutation is defined as ordering of a collection of objects. Okay. The number of permutation of n object is factorial of n. Okay. And it is defined as this. Okay. And when is equal to 0, it will not be 0, it will be 1. So that is a special situation. So factorial of 0 is equal to 1, okay, not equal to 0. So the number of permutation of k objects chosen from a group n objects is defined as this equation. Okay, so for the lifeguard example, okay, so we can simply write the equation P and K. Okay, so totally we have 5 lifeguard. Okay, and we need to choose 3 lifeguard for the 3 different lifeguard stations. So it is P35. So we pick 3 from the 5 objects. Okay, so in the cases when order matters, we should use permutation. Okay, so what does mean? What is order matters? In this example, the lifeguard example, we have 5 lifeguard and we have 3 different stations. Okay, so the stations are different. So that means when, in this case, the order does matter. Okay, so if I say we need to pick 3 lifeguard from these 5, and then we assign them in 3 same stations. Okay, if the stations are the same, then the order will not be matters. Then we cannot use permutation. We cannot use another equation, which is called combination, which we'll touch in a moment. Okay, remember here, we use permutation when order matters. Okay, so when order matters, use permutations. And the equation for permutation is this one. Here's another example. So we have a lock consists of 5 parts. Okay. And can be assembled in any orders. Quality control engineers.
Excuse me, Professor, I have a question.
Sure.
In the previous slide where n factorial is given a value, what is the L notation in that equation?
I'm sorry for that. It's just dots, the L, where is it, L?
It says n factorial equals n times
here,
n
right?
minus 1.
Yeah, here just means
n minus 2
minus 2.
L.
Yeah, L just, it should not mean show L, it's just n minus 3, n minus 4 times n minus 5 and so on. Okay? Until you get 3, 2.
Oh, okay.
Okay. Yeah, print the PowerPoint into PDF, sometimes the character will change. Sorry about that. But here L is just, any things in between. Okay, in between. Until you get 3, 1, 2, and 1. Okay?
So we could just put the little
little dots.
periods.
Yeah.
Yeah, okay.
Yeah.
Dot, okay.
Dot. Yeah.
Thank you for that. I was trying to understand and I didn't get it.
Sorry about that. Sometimes it shows weird character, and it is very hard for me to change that. I will, discuss that during the class, during the lecture. Okay, go back to the log problems. So we have 5 parts.
Sorry.
Yeah.
Sorry. Like for that equation for like the 3, the 2, and the 1, is it like the same thing? Kind of with like the dots, or?
Yeah, you just times n minus 1 times n minus 2 times n minus 3. So every one times is 1, 1 minus the
Right.
2 until you get 3, you get 2, and you get 1. That's the definition of
Okay.
factorial of n. Okay. For example, here, factorial of 5 is equal to 5 times 4 times 3 times 2 times 1. Okay.
Right.
Yeah.
Standard factorial
Yeah.
operations, right?
Yes, standard. So for that log, they have 5 parts and can be assembled in any order. The engineer want to test each order for efficient of assembly. So how many orders are there? Okay. So in this, we have 5 parts. We just go slow to make sure everybody be with us. Okay. So 5 parts, P1, P2, P5. Okay. And again, we can think this as 5 steps. Step 1, step 2, step 3, step 4, and step 5. Okay. So for the first step, we have 5 parts to choose. Okay. For the second step, we have 4 remaining. For the third one, we have 3 remaining because we picked 2 already, and so on. Okay. Right. And you can also use equation for permutation. Okay. So for this experiment, the order does matter, right? The order does matter, and we try to pick 5 parts from the total of 5 parts. So that is P5, 5. So the n is equal to 5, and the k is equal to 5. Okay, so you can simply use the equation for permutation to get the right answer. Again, the order of the choice is important. We use permutation. Then let's look at combination. So combination is similar to permutation, but only use combination when the order does not matter. Okay, let's look at in this case. So we have start considering a permutation of 3 letters, A, B, C, D, and E. Okay, so this is 5 letters. Okay, we pick 3. And based on the equation for permutation, we have totally 5. If we pick 3, when the order does matter, we use permutation equation, right? And this is permutation of 5, factorial of 5 times factorial of 5 minus 3. Okay, so we have 60 possible outcomes, like we can see from here. Okay, totally 60 outcomes. So combination are unordered collection of objects. Okay, and again, permutation is for order. Okay, the number of combination of k objects chosen from a group of n objects is c and k. Sorry, again, here it's not right. It should write as c k n. C is for combination. So we pick k objects from a group of n objects. when the order does not matter or unordered collection. Okay, the number of So here is a special situation. The number of ways to divide a group of n objects into group of k1, again here should be k2 dot 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 kr. Okay, where k1 plus k2 plus k3 plus dot 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 plus kr is equal to n. All right. So in that case, we should use this equation. Okay. So the factorial of n over factorial of k1 over factorial of k2 times factorial of kr. Okay. So this is a special situation we're gonna look at in a moment. Right. So in this example, 3 members of 5-person committee must be chosen to form a subcommittee. Okay. How many different subcommittee could be formed? Right. In this case, we still pick 3 persons from a group of 5. So in that case, it's similar to the lifeguard situation. But difference of this example from the lifeguard example is the order does not matter. We only need to pick 3 from the 5 to form a subcommittee. But that's same rule for this 3 person picked. Okay, so the order does not matter in this case. So that tells us we should use combination, not permutation. Right? So that's gonna be C. C is for combination. 3, 5. So we pick 3 from the total 5 choice. Okay, then we use the equation for combination. Again, the equation is this. And minus k. So if we change this question, if we say we choose 3 persons to form a subcommittee, and for that subcommittee, the 3 persons have different roles, like the chair, the vice chair, and the secretary. If that's the case, the order will be matter. Then we will use permutation equation, not combination. Okay. Let's compare the equation for permutation and combination. So this is C and K, right? And for P and K, it will be this. Factorial of n over factorial of n minus k. Okay, and we can see this equation partly similar. This part, right, is actually P Kn. All right, so you can simplify or write C and K into another way is equal to Pkn over factorial of k. All right, and we can see from here, Pkn will be larger than Ckn. Right, so when order doesn't matter, we use Pkn, and the possible outcomes will be more than Ckn. Right? Okay.
I have a question, Professor.
Sure.
When we do these problems, is it going to tell us to use combination or permutation, or is that for us to decide?
Or it is for you to decide if the order matter or not. Okay, yeah.
What's a good rule of thumb to let us know if we should use the combination equation or the permutation?
Yeah, we're gonna discuss several more examples, and you will have an idea when to use which equation. Okay.
Okay.
All right.
Thank you.
Okay. Here, six lifeguards available for duty on Sunday afternoon. There are 3 lifeguard stations. Okay. In how many ways can 3 lifeguards be chosen here without regard to their order? So in this question, it tells us do not consider the order. Okay. When the order is not considered, we're gonna use what? Permutation or combination. Combination, right? Remember, without order, combination. When the order doesn't matter, we use permutation. Okay. Then simply we're gonna write C. How many total? We have 6 lifeguard. How many to choose? 3. Okay, so it's C3, 6, which is equal to, just plug in the equation. Okay, all right. Another example, a certain event, 30 people attend, and 5 will be chosen at random reserve prizes. Here, the prizes are all the same. Order does not matter. Okay, order does not matter, combination. Okay, combination, how many in total? 30. How many to choose? 5. Okay, so C5, 30. Okay, so these 2 questions, tells us directly order does not matter. Okay. The next example, we're gonna use the special equation, special situation, which is here. Okay, so the number of ways to divide a group of n subject into group of K1, K2, KR, and when K1 plus K2 plus KR is equal to n. Okay, like in this example, a die is rolled 20 times. Okay, and 3 times we have 1. 5 times we have 2. 4 times has 3, 2 times have 4, 3 times has 5, and 3 times has a 6. Okay, so we have 20 times. We roll the die 20 times. Okay, and these are all the outcomes, but we do not know the order. But we only know 3 times of these 20 times we have 1. Okay, and you know this 3 plus 5 plus 4 plus 2 plus 3 plus this 3 is equal to 20 total. Okay, so then we're gonna use that special equation. The possible outcomes will be factorial of n over factorial of k1 times factorial of k2, so on, factorial of KR, right? So n is 20, K1 is 3, okay, factorial of 3, K2 is 5 times KR is 3. Okay. All right, the answer is so 1.955 times 10 to the power of 12. So many ways. Okay. Another example, we have a box of candy. We have 6 candies, okay, and 4 red and 2 green. Okay, we select 2 candies at random. What is the probability that exactly one is red? Okay, so let's look at how this answer is given. So we pick 2 candies, and the first pick and second pick doesn't really matter. Okay, so the order in this choice is not important. So we use combination. We pick 2 from the total 6, so we should use CEE306. And we have 15 ways to choose 2 candies out of the 6. And then let's see how many ways to choose 1 green Okay, we only have 2 green Okay, so we pick 1. The order doesn't matter, so we have C12. We have 2 ways to choose 1 green candy. And similarly, we have C14, 4 ways to choose 1 red because we have 4 red candies. Okay, so we have 2 times 4 equal to 8 ways to choose 1 red and 1 green candies. All right, so the probability will be 8 ways to choose 1 red and 1 green over the total possible ways, which is 15. So 8 will over 15. Okay, that's one way to do that. That's other ways to do. Okay, for example, let's say we know we have 15 total ways to pick the candy. Okay, C26, 15 different ways. And what are the possible outcomes? So we could have, 1 red and 1 green. Okay, and we could have 2 red. And what are the possible outcomes? 2 green, right? We could also have 2 green. So these are the only outcomes when we pick 2 candies from this box. Then we can calculate the probability for each. The easiest one is, what is the probability we get 2 red candy? Right? We have 4 red candies. The chance we get 2 red candies will be C2, 4. The order doesn't matter. Okay, we pick 2 red candy from the total 4 red candy. It's C2, 4. So which is equal to 6. The chance we get 2 green candy. Okay, how many possible ways we get 2 green candy? Look at the box. We only have 2 green. Okay, so the ways we get 2 green candy from the box is how many? That will be only 1 way. We have 2 green candies and we pick 2. So C22 is equal to 1. All right, and then the chance we get 1 green and 1 red will be remaining 15 minus 6 minus 1. So we have 8 ways. So 8 over 15. Okay. All right. So far we have discussed combination and permutation. You need to first figure out if the order does matter or not. Sometimes it is very easy. The question will just tells us the order matter or not. Sometimes you need to think carefully which equation to use. Okay. After that, it just be pretty simple. Plug in the number for the equation of combination or permutation. Right. So any questions so far before we continue for the next part? Okay. All right. So this is the old example showing us for a certain rod, I believe, 1,000 rods. It measures the diameter and the length. Okay. So some of them are short, some of them are long, some of them are thin or thick. Okay. So this is the distribution of this 1,000 rod. Okay. So what is property? The rod is too long. Okay. And the rod is too long here. All right. So it's too long. So it's gonna be 2 plus 25 plus 13 over the total number of rods, 1,000. So this is the probability the rod is too long. All right. So look at the next question. Will your answer change if you know that the rod is too thick already? Okay. So if you know the rod is too thick, okay. So how many rods are too thick? Only 5 plus 4 plus 13. Okay. So this is equal to 22 rods. So only 22 rods are too thick. So out of this 22, which is already too thick, what is the chance the rod is too long? Okay. So how we can calculate that? By intuition, we know probably if we know it is already too thick, out of these 22, how many are too long? 13. Okay, so out of this 22 rod, which is too thick, 13 of them are too long. Right? So the probability will be equal to 13 over 22. That is an example of so-called condition probability. The condition is it is too thick. Okay, so under that condition, it is too thick. What is probability it is too long? Okay. All right. So section 2.3, conditional probability and independence. Look at the definition. A probability that is based on part of the sample space. Part of the sample space. For example, we know, it is already too thick. Okay, so part of the sample space is the rod which is too thick. Then it is called conditional probability. Okay, so let A and B be events, and the probability of B not equal to 0. Okay, then the conditional probability of A given P. Okay, we see that PA given B. So the line means given here. Okay, so the probability of A given B occurs is equal to PA half circle facing down is called what? And. Okay, so equal to PA and B over PB. All right, so we can think in this way also. So we have two events. One is A and one is B. Okay, so PA and B is this part. Okay, this part is A and B. Both A and B occurs, so that's the intersection of these two circles. Okay, so this part is the intersection, right? And PB will be the whole circle of B. Will be this part. That is PB. All right, so you can have an idea what is conditional probability. The probability of A occurs given B is equal to PA and B, which is the intersection here, over the circle of PB. So the condition is PB. So under the condition PB occurs, which is within the circle of B. All right. Okay.
Professor, I have a question again.
Yes.
Is that P times A over B?
Where P times?
Where it says it's given? What's that line?
The line just showing us, the line just means given. It's not time. We write PA, the line B. That means under the condition B happens, what is the property of A?
Okay, I got it. Thank you.
Okay, okay, yeah. Go back to the previous example. I think last time we discussed that. So we have aluminum can, right? And we have floor on the can. The probability the can has a floor on its side, 2%. The floor on top, 3%. Probability on have a floor on both side and the top is 1%. Okay. So what is the property that a can will have a floor on the side given it has a floor on the top? Okay, looking for the words given. So given is the condition. So under the condition, the can has a floor on the top, the question is asking what is floor on the side. Okay, so again, we can use the chart and the equation to figure that out. Okay, so that circle, let's say we have a floor on the side. And for this circle, it said it has a floor defined as floor on the top. Okay, then let's put in what the question tells us already. The problems, a can has a floor on the side is 0.02. Okay, on the side, so this is 0.02. Property has a floor on the top is 0.03. That whole circle. What's wrong with this? And property has can on both side and top is 0.01. So this intersection is 0.01. Okay, and then we can figure out, on this area, for example, which is it has a floor on the side but not on the top. So that area will be 0.02 minus 0.01. Okay, and in these areas, okay, will be 0.03 minus 0.01, which means it has a floor on the top but not on the side. Okay, so we can figure that out first before we answer the question. Under the conditional property, the question is asking this. What is the property it has floor on the side given the line is for given it has a floor on the top is equal to it has a floor on both the side and the top over it has a floor on the top. All right, so from the chart, we're gonna know P, S, and T will be what? Will be in intersection, right? Intersection here. This part will be 0.01, as the question tells us, 0.01. Over PT, the property has a floor on the top, which will be the circle of T, this part. And this part is 0.03. So that's 1 over 3 chance. Okay. Questions for this? right. Again, this part, the intersection will be P, A, and B. Okay, and this part, the whole circle will be P, PB. Okay, so this whole circle of B will be PB. Okay, so the conditional probability PA given B, right, will be PA and B over PB. Okay, from this diagram will be PA and B, this intersection over PB, which is that circle. All right, so this is an introduction of conditional probability. Okay. Yeah, so today we introduce some brand new ideas, combination, permutation, and the conditional probability. So I bet gonna need some time to digest. Okay, so let me know if you have any questions after the class. Okay, let's continue. Independence. So two events A and B are independent if the probability of each event remain the same whether or not the other occurs. Okay, I think we touched this idea a little bit before. If PA is not equal to 0, so does PB, then we say A and B are independent if PB given A, so B given A is equal to PB, and PA given B is equal to PA. All right. So that means these two events does not have intersection. Okay. So the conditional probability is equal to the probability itself. Okay. If any of PA and PB equal to 0, then they are also independent. Okay. All right. Okay. So the dots always become K in the PDF. Sorry about that. Okay. So let's say we have n events, A1, A2, An, and they are independent. Then the probability of each remains the same no matter which of the other occurs. Okay. For example, we toss the coin twice. Okay. If we define events A is equal to is head on the second toss, and event B is we have head on the first toss. Okay, and let's see if these two events are independent or not. So first of all, let's figure out all the possible outcomes. If we toss a fire coin twice, okay, so the first pick we could have head, the second tail, so that's the first, and for each of the outcomes of the first pick, the second pick, we also have head, tail, head, tail. Okay, so we have these 4 possible outcomes. Okay, and each of them has 25% of chance. Okay. So let's check the probability of A given B. So B is we have head on the first toss. Okay, which is here. We have head on the first toss. Okay, so PA is the head on the second toss. Okay, which is here. Right. So PA given B will be 50%. So that is
Professor, I'm trying to understand the notation in that box that you're sketching next to. There's a P, and then there's an A, and there's a straight vertical line.
Oh,
What does that
mm,
vertical line represent again?
well, vertical line. The vertical line means given the condition.
Oh, okay.
Given the condition of B. What is the property of A?
I think there's something wrong with the sounds.
Yeah. I also heard that. Anybody, please mute your microphone, please. Sorry. Anybody, don't know what happened.
Professor, I don't know if this is like something you want to do. Like, oh, I think it stopped.
I think, yeah,
Oh.
I think it's just coming from your side, Professor.
Yeah, maybe,
Had that mic on.
You might want to restart the recording if it, or like the Zoom session maybe.
okay, maybe I'm gonna log off and be log in again.
Maybe that'll make it stop.
That
Not sure.
that might help.
Okay, so yeah, sorry about that. I will stop the meeting and then we're gonna start a meeting again. Okay, I don't know what happened. That's the first time we do here. All right, I'm gonna log off and then log in again. So please come back. All right.